Okay, so today we've got a fun video, if you're a mathematician that is. We're going to be integrating the secant of x with respect to x, but in three different ways. Now, when I originally started this integral, I was thinking, there's no easy way to do this. There's no formula that I could remember. There is a formula, it exists, but there are multiple ways of integrating this, as we'll see. I have a favourite way, and it's not the easiest way, so first of all, let's start with the easiest way. What we're going to do is we're going to immediately multiply the top and bottom by secant x plus tan x. So we get secant x multiplied by secant x plus the tangent of x all over secant x plus tangent of x dx. And the nice thing about this is that it's very simple to evaluate. If we let u equal secant x plus the tangent of x, we get that du is equal to secant x tan x plus secant squared x, all multiplied by dx. And this is precisely what we have on top, because if we distribute this secant x here, we just get secant squared x plus secant x tan x. So after performing this substitution, the integral simplifies quite nicely to just the integral of du over u, which is just the natural log of the absolute value of u plus an arbitrary constant of integration. This is the first method. This obviously simplifies down to the natural log of secant x plus the tangent of x plus the constant of integration. Here's our answer. Like I said, this is definitely the easiest way. It's not my favourite way, we'll get onto that in a second. The next method is going to be the method I actually used to first integrate this this function. Let's start off, let's rewrite the integral of secant x dx. Of course, secant x is just 1 over the cosine of x with respect to x. And in this step, it's hard to see that multiplying by secant x plus tan x is going to simplify this. It's hard to see at first, at least. But this one's a bit easier to see. If we multiply top and bottom by the cosine of x, we get the integral of cosine x over cosine squared x with respect to x. Now, of course, sine squared plus cosine squared is equal to 1. So cosine squared is nothing other than 1 minus sine squared. So we get the integral cos x over 1 minus sine x, sine squared x, sorry, dx. And then we can perform a simple substitution. Let u equal sine x. Du is nothing other than the cosine of x dx, which we have here. We just substitute now. We get the integral of 1 over 1 minus u squared du, which is simply the integral of 1 over 1 minus u 1 plus u du. We're going to have to use partial fraction decomposition to solve this integral, but let's just go right ahead. 1 over 1 minus u times 1 plus u is equal to a constant a over 1 minus u plus a constant b over 1 plus u, which implies that a multiplied by 1 plus u plus b multiplied by 1 minus u is equal to 1. Now at x equals 1, this b term disappears, so we're just left with 2a is equal to 1, so therefore a is a half, and substituting negative 1 eliminates this term. We get b times by 1 minus minus 1 is 1, so 2b equals 1, therefore b is also 1 half. Okay, you can go through this thoroughly, check this yourself. I was just sort of going through it without writing it down, but that's fine. So we get that this original integral here is nothing more than the integral of 1 half over 1 minus u plus 1 half over 1 plus u du. Now, we can factor out the half if we want to, but I'm sure you can all integrate this by now. This is just nothing other than 1 half times the natural log of the absolute value of, because we've got a negative u, we need to put the negative in front like that, 1 minus u plus 1 half the natural log of 1 plus u plus the arbitrary constant c. Factor out the 1 half and rearrange. We get the 1 half times the natural log absolute value 1 plus u minus the natural log of the absolute value of 1 minus u plus c. We can use logarithmic properties to get the final answer of 1 half natural log of 1 plus u over 1 minus u plus c. We substitute back in the original u, which was sin x. 1 half natural log of 1 plus sin x over 1 minus sin x plus the arbitrary constant c. And obviously this is in a much different form to the other answer here, but they are in fact equivalent. I'm not going to prove their equivalence now, but it's an exercise for you. If you have a graphing calculator, you can prove it that way. I think they aren't separated by, they're not different by a constant. I may be wrong on that. You'll have to check, but in terms of integration, these are the same function. This brings us on to my favourite method, the final method. Let's just hop straight into it. We've got the integral of secant x dx, and we're going to be using complex numbers to integrate this. Now, the cosine of theta can be defined in terms of complex exponentials, which is simply e to the I theta minus e to the minus I theta over 2. Therefore, the secant of theta is just the reciprocal of this, namely 2 over e to the I theta. Sorry, this should be plus e to the minus I theta. If it was minus here, that would be obviously sine theta. So let's just substitute this in for secant x to begin with. Get the integral. Let's take the 2 to the front. 1 over e to the I theta plus e to the minus I theta d theta. I should probably stick in the x world. It's just a dummy variable, it doesn't really matter. Let's keep it with theta. X is theta, so dx equals d theta. I'll use theta for complex numbers like this, why not? And then we can substitute x at the end. It doesn't make a blind bit of difference, to be honest. Now let's multiply top and bottom by e to the I theta, namely to get rid of this nasty exponential here with a negative right there. We get 2 times the integral, that was crap, 2 times the integral of e to the I theta over e to the 2 I theta plus 1 d theta. Let's do a substitution. Let u equal e to the I theta. So du is just I e to the I theta d theta, which is just I u d theta. So we get, also let's know that e to the 2 I theta is just e to the I theta squared, which is just u squared in this case, using this substitution. We get 2 times the integral of u over u squared plus 1 times 1 over I u du. The u's cancel, and the 1 over I is the same as negative I. So let's bring that to the front. Negative 2I times the integral of 1 over 1 plus u squared du. And if you watch my videos frequently, you'll recognize this, because I did a video on this integral here. This is simply the arctangent of u when we integrate this. So we get the final answer of negative 2I times the arctangent of u plus c. What was u? U was just e to the I theta, e to the I x, thanks to this substitution. So we get finally our final answer, negative 2I times the arctangent of e to the I theta plus the arbitrary constant c. And I think this is quite a beautiful answer. I have verified this. I plugged in bounds to this. By the way, this is the complex arctangent extended to include complex numbers, as the domain of this arctangent function has been extended essentially. But the point remains, you can, if you want to, use the definition of the complex tangent to prove a formula for this arctangent. I'm just going to leave it in this form. But this is also equivalent to this and this. These are all valid answers, but I would recommend, if you're on a test, not using the complex way. This is a fine answer, and so is this, but I would use this because it appears simpler. I hope this video was helpful, and I hope you enjoyed it. It was definitely my longest video, but I thought I'd dedicate some time to this integral because to a newcomer this isn't immediately obvious. But I hope you enjoyed.